let me take you through what I cover in Unit 4A, which is the force aspect of when multiple forces are acting on a body. I know that might sound a little redundant, but it really isn't. The main emphasis that I cover here are free body diagrams and how to do force problems. Now, first off, a free body diagram just simply identifies all the forces acting on a body. And what's really important is, if you don't get the free body diagram right, you probably won't get the problem right. It is a very critical piece of information. I want to emphasize that only forces are shown on the free body diagram, nothing else. Now, I'm going to give an example of some free body diagrams in just a few minutes, and I'm going to put other information on them, but that's not the so-called official free body diagram. Force vectors always start on the body, so they begin on the body, and they point away. This is pretty important. And you'll see that I don't stack them. If there's multiple forces acting in the same direction, I kind of put them side by side. It's kind of important, or this is helpful, that the vectors should be scaled. And when you're just sketching a free body diagram on your own, it's not that critical, but a lot of times the problems have you draw the forces on a grid. And so it's really important that if one force is twice as large as the other, that you draw the arrow twice as large. The biggest thing about free body diagrams, and this is probably one of the biggest challenges that I face with my students. A free body diagram tells us nothing about motion. If the body is moving, if it's at rest, if it is moving, it tells us nothing about that. And so that's a real important idea that needs to be emphasized as you're introducing free body diagrams, and really throughout the year. So let me give you a couple of examples of a free body diagram. Here is an example of a book that's sitting on the table. So it's at rest, no velocity. Here is a book that's sliding across ice. So it's on a frictionless surface. That's the idea of ice. So my free body diagram, just a dot, and from this dot I'm going to draw the forces that are acting on the body. Well, we have gravity acting on the body, Fg, and then we have a force from the table pushing up called the normal force, and that's all my free body diagram looks like. So this is my official free body diagram, and if I drew vectors up here on this picture, that would be a working copy, which is perfectly fine to put any information you want in a working copy. So on this book that's sliding across the ice, I still have gravity acting on it. The ice is pushing it up. That's a normal force. And then that's it. We have no force that's continuously pushing. I don't care about the force that got it moving. It's already moving. These are the same. And this is what I was referring to in terms of the free body diagram tells us nothing about motion. This book is moving because we're told that, but from the free body diagram, we wouldn't know that it's moving. And this is an important thing to recognize, that when kids see this free body diagram or that, they don't know what's going on. All we know is that we are in equilibrium, which means we are at rest or moving with a constant velocity. That's all these pictures are telling us. And quite honestly, that's all the intent for the free body diagram is. So let me just take a second and kind of identify some of the common forces that we run into when we're doing these problems. Probably one of the most common is Fg, force of gravity. Every object, if it has mass, and everything that we deal with is going to have mass, has a gravitational force on it, an Fg. Now, this is also referred to as the object's true weight. This is an important term to remember because it does come up periodically throughout the course. Fg is simply equal to the mass of the object times the acceleration due to gravity. Another common force is a normal force. Now, there's also different notations for this. For Fg, you can write it as W. You can simply label it as mg. Normal force, I've seen it written with a capital N, F with a capital N. There's different ways to label the normal force and different ways to note different forms of notation. It doesn't matter as long as it's clear that we're talking about the normal force. Another term for the normal force is the object's apparent weight, and I hope I spelled that right. It's real important, apparent weight and true weight, and I'm going to talk about these two, the differences between normal force and the force of gravity in just a minute, because there tends to be a lot of confusion with that. What I call the frictional force, and that's how I label it, or just simply friction. This is a force that opposes sliding. I read that definition. That's how somebody expressed it. I read that a few years ago, and I really liked it. I always thought of it as opposing motion, and this is better. It opposes sliding. Now, to calculate the frictional force, what we do is we say mu Fn. Mu is our coefficient of friction, which is it's a type of rating. It's a friction scale between 0 and 1 on how much friction there is between two surfaces. We got a coefficient for kinetic friction while the object is sliding, and we have a coefficient for static friction. This keeps it from sliding. So this is while sliding, and the static prevents sliding. It's very helpful to keep the differences in the terms in mind as the kids are doing the problems. I'm not going to say it is ultimately critical, but it does help as they are looking at the problems and keeping straight as to what the question is asking for. Other forces that come up, tension, T or Ft, and that's just a pulling force with a rope, nothing overly critical. But these are the primary forces that we run into when we're doing these force problems. Let me just talk about for a second a few notes on some of the forces. The force of gravity is always straight down. I take points off, or I give the kids no credit if they don't draw it straight down. I'm very picky about that. The normal force is always perpendicular to the surface. It's the surface force, and so if you're on an incline, it's slightly at an angle. If you're on a flat surface, it's straight up. I already mentioned that frictional force opposes sliding, which is really important to think about. Along with the normal force, this is real important. The normal force is not equal to the force of gravity. Sometimes it is. but it doesn't have to be. This is a very common misconception. I'm going to talk about this in just a second. So let me take you through the 4 basic steps that I teach my kids on to go through when they're solving a force problem. And I repeatedly go through these throughout the year, especially when it is a problem related to forces, and I always go, what's step number 1, what's step number 2, and to kind of help them through that process. Step number 1 is to draw the free body diagram. Again, if this is the most critical step, because if that's not right, you're not going to get anything right. Now, there's kind of 2 types of free body diagrams. The so-called official free body diagram, which is the dot and just the force vectors drawn on it that I showed a few minutes ago with the book sitting on the tabletop. And then you have the working copy. So in the working copy, I include all sorts of information, and that's perfectly fine. So like the book sitting on the tabletop, I might say it's 3 kilograms, and I've got gravity, and I've got a normal force, and it might be at rest. And if I have a pulling force, I would say what that angle is. None of this on the official copy. It would just simply look like gravity, normal force, a pulling force. And so that's just a lot more information here, but this is not the official, and it's very important to keep the difference between the 2. Step number 2 is to break up all your forces into the x component and into the y component. And this is where I have them set up like a little force table. Step 3 then is to ask the question, what does my net force in the x direction equal? What does my net force in the y direction equal? For our problems, this will always be 0. It doesn't have to be in other courses, but in Physics 1, it is 0. This piece of information is from the problem. The problem will say it might be moving at a constant speed. If it's moving at a constant speed, then that value is 0. The problem might say it's accelerating. If so, then that value is ma. And so, quite honestly, the net force is equal to ma. Now, if the problem tells you there's no acceleration, then a is 0, net force is equal to 0. The 4th step, then, I tell them is to simply solve. We have all these expressions for the forces in the x and y direction. We have 2 equations. Solve for what the problem is asking us to solve for. It could be acceleration, it could be the coefficient of friction, it could be another force, whatever. But these are the 4 basic steps that I tell them to go through, with this, quite honestly, being the most important. Okay, I'd like to wrap up this topic with talking about the difference between the normal force and gravity. And I mentioned before that kids like to say that the normal force is equal to gravity, but it's not. It's dependent upon the problem. Let the free body diagram dictate that. For example, we have the problem of the book sitting on the tabletop. Gravity is pulling it down. Normal force is up. Yep, here, normal force is balancing gravity. We could have a problem where something is being pulled across a level surface at an angle from a force. Gravity is pulling it down. Normal force is pushing it up. In this case, there's a component of this pulling force also. And so we have the normal force plus that component is going to balance gravity. So here, normal force is less than gravity. A box on an incline, we have the same situation. Gravity is straight down, normal force is perpendicular, so normal force is balancing a component of the gravitational force, so it's less than gravity here again. Or, and I do this with the kids, I get a bathroom scale and I set it out and I have somebody stand on it and they read their weight, basically what the bathroom scale is reading. So if we look at the forces on the scale, we've got gravity going down, we've got the normal force pushing you up. And so when they're just standing there, the normal force is equal to gravity. Well, then I come along and I'll push down on their shoulders. And all of a sudden, the normal force shoots up real high. And it'll be like, hey, you gained weight. And they have to go, no, the force of gravity is the same. This doesn't change. It's mg. And so what happens is the gravitational force, we've got multiple forces coming down. We got the force of gravity. We got me pushing them down. So the normal force has to shoot up high to balance all that. So gravity plus whatever pushing force I'm applying downward is going to equal the normal force. So here normal force is greater than gravity. And so it's real important for them to understand this idea of normal force and gravitational force and how they are two separate forces. And whenever they start, if they automatically say normal force is equal to gravity, cross it off and say, even if it's right, cross it off and say, show me through the free body diagram that that's true. And you just be very careful about that. That is a big misconception kids often have. So that wraps up Unit 4A, talking about multiple forces on a body. I hope this provided some clarification. Good luck.